So, so the main question that sort of motivates this is how we can characterize experimental systems with high confidence. And hopefully get this working. Okay, so if we're trying to understand quantum systems, there's sort of this obvious problem, as Umesh said, that these systems are exponentially complex to describe. And furthermore, we only have access to them classically, because we're essentially classical devices ourselves. Right? We only see a few measurements of this exponentially complex quantum state. But there's also sort of more subtle problems. So for example, say we want to prepare a random bit. A natural approach might be just to prepare ket plus, so that's a state ket 0 plus ket 1, a uniform superposition, and then measure it, right? That should give you half 0, probably 1/2 1. But in practice, this isn't maybe the best way of doing it, because there could be all sorts of problems. So like an obvious problem that you definitely worry about is it might be slightly biased. So instead of exactly 1/√2 0, 1/√2 1, it could be slightly off from 1/√2. So you get probabilities slightly off from 1/2 1/2. But you might also worry about slightly more subtle problems in your experimental system. For example, maybe something about it results in there being slight correlations between the first time you extract a random bit and the second time, or between the first time and the last time. And so you'd want to worry about these kinds of problems as well. And sort of going much further, you might even worry about completely crazy problems. Like it could be that this quantum device, it's not really preparing ket plus and measuring it like you like. It's actually just, it has pre-programmed inside it a classical random string. And when you ask for a random bit, it just gives you a bit of that random string. And that's a problem, because this random string could be shared with the environment or shared with your attacker in advance. So, I mean, maybe that's just paranoid. Maybe that's a crazy error model to worry about. But I think the point is, in a realistic setting, you have to draw the line somewhere, and it's not clear where you should draw the line from the left to the right. It's not clear what the right definition of security where it should lie. And so for us, we're just going to assume that we're all the way on the right-hand side, that we're completely paranoid, and we really are worried about the case where the device was made by the adversary, in fact. And so here's sort of the security model. We're not going to try to understand what's going on inside this. Well, we're not going to make assumptions about what's going on inside the system. We're going to try to characterize it under worst-case assumptions. It's just some black box quantum device, and we'll even allow it to be made by the adversary. So now we'd like to generate a random bit using this black box device, and that's impossible, because it does have this problem that it could have the random string could have been pre-programmed. But as Umesh said, it does suddenly become possible once you have two devices that are separated from each other and cannot communicate with each other. And so this is where we introduce this CHSH game. So and I'll formulate it as a game. So here I have two devices that I'm calling Alice and Bob, and then Eve is me, Ben, whatever. So the game works like this. We choose these random bits A and B. We send A to Alice, B to Bob, and we get back X and Y. And the question is the XOR of the two responses equal to the product A and B, A times B? And so, for example, if these are classical devices, they can win with probably 3/4. They can just output X equals Y equals 0. So the XOR is equal to 0. And 3 out of the 4 questions, that's equal to the product, except if A equals B equals 1. Quantumly, you can do better. So here's a different way of showing the same thing Umesh did for the optimal strategy quantumly. So here we assume that here they have an EPR pair. Alice, depending on the question, she makes one of two outcome measurements. So on the left, she's measuring in the both in the XZ plane of the block sphere. In the left, she's measuring in this direction if she gets question 0, or in this direction if she gets question 1. And Bob is measuring either along the x-axis on question 0 or on question 1, and along the red axis, the z-axis, if his question is 0. And you can see that if they both get 0, the angle between these axes is 45 degrees. If one gets 0 and the other gets 1, the angle between the axes is 45 degrees. But if they both get 1, the angles between the axes are 135 degrees, which means that they're going to output the same answer with probably cosine squared pi over 8 if they both get 0 or one gets 1. But if they both get 1, then they get the different answers with probably cosine squared pi over 8. And that's exactly the correlations that we'd like in this CHSH game. And so that's how quantum devices can win this game with probably cosine squared pi over 8, which is roughly 85%. It's 10% better than the best classical strategy. And so this lets us test the system is quantum mechanical, but we want to go much further. So let me state the first rigidity theorem. So here we assume that these two devices share an arbitrary quantum state, an arbitrary density matrix, and they have arbitrary Hilbert spaces HA and HB, which could be infinite dimensional, and they're not qubits or anything necessarily. And they can make arbitrary projective measurements on these states to determine their outcomes. And then the theorem we show is that if they win this game with probably at least roughly cosine squared pi over 8, so cosine squared pi over 8 minus epsilon, then up to a local basis change, up to local isometries, a separate isometry in each half, the initial state is root epsilon close to the ideal state, the EPR pair, possibly in tensor product with some other junk. And furthermore, their measurements are root epsilon close to the ideal measurements. And the way you can quantify that is you, I mean, we don't actually know what their measurements are, what the, I mean, they could be doing anything on areas of the Hilbert space on which the state has no support. And so the way we quantify this is we just say the effect of their measurements is the same as the effect of the ideal measurements, up to square root of epsilon error again. This is the kind of theorem which says that once we characterize the probability of winning, we can characterize the strategy. And this is simple to prove. I'll skip the proof. It's sort of it's almost an immediate exercise. You just have to look at the projective measurements that they make. So that gives you two hyperplanes, and now look at the dihedral angles between these two hyperplanes, and that gives you the qubits, and therefore you can grind through some algebra. But I want to say more about the bigger theorem, actually, in a minute. All right, so how do we use this theorem? Basically, we just apply a simple statistical test. So what you're going to do is you're going to run this game 1,000,000 times, for example, and you're going to see how many games did they win. And the point is, certainly classical devices could win 85% of the games. It's just exponentially unlikely. All right? They'd have to get extremely lucky. And so we can show, instead of, if they win like, all right, so I'm kind of calling it omega star from now on. So that's 85% or cosine squared pi over 8. If they have a high probability of winning close to the optimal fraction of games, then that means that at the start of a random game in the middle there, when that game began, they had to have had a high probability of winning that one game just by statistics. There's nothing quantum here. And therefore, apply the previous theorem. They have a high probability of winning this one game. Therefore, by the previous theorem, they had to be using an EPR pair in that one game, or square root of epsilon close to an EPR pair. And so that says that so the assumption here is that they've won 85% of 1,000,000 games, and the conclusion is that they have one EPR pair in a random game. So. I mean, it's interesting, I guess. It says that they're quantum mechanical, and they have at least one bit of entanglement, but it's rather a pretty disappointing theorem, I think. Yeah.
You said it says they're quantum mechanical, but you're assuming they're quantum mechanical to do the analysis.
I'm assuming they're quantum mechanical. It says that they're not classical. Sorry.
Oh, okay.
That's what I meant. So really, we'd like much more sophisticated tests. We'd like to be able to say that if you play a bunch of games and if you pass all these tests, then not only do you share one bit of entanglement, but you share lots of entanglement. And that would be something that we could actually leverage and use to prove more theorems. And so here's sort of the main theorem in a reasonably quantitative way. So the setup is going to be, I'm going to play little n games at a time, just in sequence, one after the next, and then I'm playing capital N blocks of these games with the two devices. And so the assumption of the theorem says it's the same as before. If there's a high probability that they win close to the optimal fraction of the games, close to 85% of the games, then when you look at a random one of these blocks of little n games, at the beginning of that block, they had to have little n EPR pairs. And during that block, when they played that block, they had to be measuring those EPR pairs one at a time according to the ideal strategy. So winning them with probably cosine squared pi over 8 with these measurements.
Can I ask a clarification question?
Yes.
I'm confused between sequential and parallel. The little n, are they playing it in parallel? Or
Sorry, everything's sequential. I just broke it up in this way. Yeah. So this kind of theorem really does give us a way just of giving us statistical test of seeing that they do share lots of entanglement, at least little n EPR pairs worth of entanglement based on a statistical test. It's kind of inefficient. So to make this theorem work, we need capital N to be polynomial in little n. So in theory, it's efficient, but it's not a great polynomial, I don't think. And second, I didn't say how close this is here. And again, that'll be polynomial in epsilon, but it'll be like epsilon to the 1 over c for some constant c. And c is like something quite impractical.
Ben, can you say again how this theorem improves over the last one? Is it that with this one, like even after the test is over, you still know that there's lots of entanglement in the other blocks? Or?
No, I mean, in both of these tests, or in both of these theorems, they're sort of retrospective, the way I'm describing it, in that because by the time you get this conclusion, you've played all the games, so you've destroyed all the entanglement.
All right.
So no, the interesting thing of this theorem really is that it gives you a way of guaranteeing that you have n bits of entanglement at the same time.
Oh, okay, rather than just one.
Which is, I mean, it's very intuitive. You think in the previous theorem you would too, but
All right, good.
This is just saying that.
Good. Yeah.
Yeah.
Just for me to understand this retroactively, what it formally means, does it mean that if you don't have this many entanglement bits in the very beginning of the whole experiment, then your probability of succeeding in the experiment is very low? Is that actually what is being proven?
Well, that's certainly true, and that's a corollary of this. But I think this is.
But the thing is that I don't see a definition of this because after something has, I mean, classically you can make a history of what happened, but quantumly, if you run some experiment, you can actually not really necessarily say what was true at an earlier point because you can't copy that information to look at it later. I mean, it's not necessarily a well-defined statement to say earlier in this execution there was this much entanglement, because if later I make a measurement that's changed what, I mean, the quantum state is gone. I see no.
But it was
way
there.
of
I mean, I think it's perfectly fine to say that because it was there. So maybe the assumption isn't clear. So I'm not saying if you win 85% of the games. I'm saying that if
it's not clear. Imagine this game that I have 2 qubits.
Yeah.
Unentangled
Yeah.
In the beginning. Then I run a process. In the end, I measure whether these qubits are in the. I measure them in the bell bases.
Okay.
And I get some outcome, and then they are suddenly entangled. And actually, in a sense, like this entanglement. So I'm measuring that they were always entangled, because they were in the beginning in a superposition of different possibilities how they were entangled. So it's not really clear whether it's
local operation here. The answer above is
no, I'm
correct.
just talking about the fact that it's not well defined, at least for me, what it means that something was true when we have measured and therefore destroyed the information of what was actually the case earlier.
Well, I think it is. I think it is okay to say that at a particular time in the protocol there was entanglement, even if later on it's gone or it's created later on or something crazy happens later on. I'm saying if you interrupted the protocol after a random, at the beginning of a random block, if you stop the protocol there and looked at whatever the quantum state is, there is some quantum state at that point.
But then if you're interrupted, you don't know yet whether the experiment
That's right.
will succeed.
That's right.
So
I agree. No,
we can talk
that's
about
right.
this offline.
Huh. No, that's the problem,
It's
right?
not saying anything about the possible prediction of the experiment. about the possible state.
Exactly, but the state is already gone at the point he talks about it.
That's fine.
No, that's not
Making
fine.
the claim
Well,
about
it might be fine.
The information, it's physically not meaningful what the state was if we don't measure it.
So, but, I mean, if you look at the statement of the theorem, there's an if and a then, right? And so the if is a probability of what will happen if you make all these measurements. And that can be, that statement is well defined even at the beginning of the protocol,
Yes.
right? And so, so if you think of this as a statement then at the beginning of the protocol, that in the future, once these measurements are made, here's a statement about the probability of the outcome, right? Then is well defined at that point, and everything's fine.
Yeah, but that's not the thing we were talking about. I think it was farther below.
Well, I think you should think in the counter to the thing. Like you should think that if it was not entangled,
Well, the
then
problem, the thing I have a problem
then
with.
with high probability you would get something else.
All right,
So that's
If you light a match and it burns, you can say that it was a good match, even though after it
That the
burns.
claim is if in the beginning we don't.
all right, thank you.
that's the counter.
What I'm saying is there was at some point in the experience.
And let me maybe move on a little bit. So I like Daniel's interpretation of this. That's a good way of putting it. You have to say how do you establish this initial assumption, and maybe that's not clear. You're gonna have to think about how you get that assumption in the first place. But anyway, let me just say a little bit more about what this means formally. So. Formally, the way we express this kind of theorem, and that's half the work in proving lots of these theorems, is just stating them carefully, is we express it all in terms of superoperators, so, and trace distance. So what I mean is, say you have a two-outcome projective measurement, so you're making measurement with these projections, pi and pi complement. That corresponds to the following superoperator, where it takes a state rho, it projects it by pi, and say that's outcome 0, it adds a classical register in 0, and then it projects the same state into pi complement, and adds, say, a classical register 1. And so this is a superoperator that describes the measurement, pi 1 minus pi. And so for us, we have this superoperator here, that EA hat, that describes the ideal CHSH game. And so in the ideal CHSH game with probably 1/2, you input coin 0, so that's his first register, and then you make some projective measurement. Alice makes some projective measurement, some ideal projective measurement, and then there's some outcome that corresponds to the measurement. And so this is the ideal superoperator, for which I'll have this hat notation. But of course, she can have sort of an arbitrary superoperator. And so the conclusion of this theorem that says that the two devices strategy is close to the ideal strategy, what it really means is that up to these isometries that embed their Hilbert spaces into a tensor product of n qubits with another Hilbert space, their actual superoperator here for the two parties for the first, say, j games is almost applied to the initial state. Rho is almost the same as the ideal superoperator applied to EPR pairs in trace distance. And this should be true for every j from 1 to n. That's what the conclusion of the theorem really says. Okay, so that's a little bit technical, but I just want to make it slightly more precise too. All right, so. How do we prove this kind of theorem? It really has 4 steps. The first step is a bit of statistics, so just classical statistics, sort of martingale kind of things. So first of all, we say that basically, if you have a probability close to 1 of winning about 85% of the games, then in a random block of games, it must be the case that you win every single one of those games with probably 85%. That's false. But you win every single one of those games with probably 85% most of the time. So for most of the previous games, you're going to win the current game with probably 85%, which means I can apply the single shot CHSH game rigidity theorem. And so therefore, this says that in a random block of n games, we're going to every single game is being won with probably about omega star minus epsilon, and so we have qubits. And here already, just to get the statistics working, we've already lost like a quadratic factor. So little n, to get this working, we need to expand the system by expand the number of games quadratically, just by statistics. Okay. All right. So now we have these qubits, but they they're all messed up. Like they overlap each other potentially. The qubits you're measuring in different games, and there's some history dependence potentially. Like the qubit you measure in game 2 could be either of these 2 red qubits, maybe, like depending on the outcome of game 1. And actually, there's 4 outcomes of game 1, so there's 4. I should have drawn 4 of them. The qubit you use in game 3 the location of the qubit you measure in game 3 could depend on the outcomes of the first 2 games. So again, there could be lots of different ones. And the most interesting step of the proof is actually showing that these qubits don't overlap each other at all, intuitively. So actually that they lie in tensor product with each other. They're independent, but there's still history dependence. And then the last step of the proof sort of glues these different transcripts together to show that there's no history dependence. So you measure the qubit, this black qubit for game 1. You measure the red qubit in game 2. Independent of what the result of game 1 was, and then in game 3 you measure the blue qubit independent of the previous results. So let me say something of the most interesting step, which is how we determine a tensor product structure in this big infinite dimensional, completely amorphous Hilbert space. And let me first say a little bit about what could potentially go wrong and what we worry about when you try to come up with these kinds of arguments. And maybe one thing you worry about is whether these pictures are accurate, which they're not really. But let me just try to draw some pictures anyway to hopefully give some intuition. So say we play the first 7 games, and these qubits that they use, they overlap slightly. Like they can overlap by like square root of epsilon at least, because they're not exactly in EPR pairs, which would be monogamous. They're only close to EPR pairs, which are not exactly monogamous. But then the problem is that the errors, these square root of epsilon errors, could keep on accumulating, and maybe in the last game or game 8, whatever, there's suddenly a huge overlap. So the location of the qubit you measure in game 8 could overlap completely with the location of the qubit that you measured in game 1. And then you would not have this, then this theorem would be false, because the theorem says that everything is in tensor product. And so we need to show that actually errors do not accumulate. That's one thing that we want to show, and this isn't so easy. I mean, because it seems like they can. So for example, here I have 5 qubits. Say I start with 5 EPR pairs, and in the first one you measure mostly the first qubit, except you have square root of epsilon error on the last qubit. On the second one you measure mostly this blue qubit, except you have square root of epsilon error on the last qubit, and so on. And so it doesn't take too many rounds before you get a ton of error accumulated on this last qubit, which could have moved it around into some other position in the Hilbert space. And so this is one way that errors can accumulate. You also worry about, because we're measuring, errors can accumulate because of the measurements, right? So when you measure a state psi, with projection pi, you get the state pi psi and then renormalized. And so, for example, if there's some small error, and if this measurement outcome occurs with probably 1/2, then the error is going to be renormalized as well. It's going to be blown up by a factor of √2. And so suddenly a small error, a square root of epsilon error, has suddenly become a square root of 2 epsilon error. And that's just after one measurement. And so if we're playing little n games, it's blowing up exponentially fast. So that's obviously bad too. A second problem, sort of, when you try to analyze it, is that if you try to fix the first game, it's going to mess up the second game. So what I mean is, we know that game 1 has probably omega star minus epsilon of winning the first game, and say we also know that the probability of winning the second game condition on the outcome of the first game is also omega star minus epsilon. So now we can apply the theorem. We can apply the one-shot rigidity theorem to the first game. So we know that at the beginning of the first game, there's square root of epsilon close to having the APR pair that they're measuring in this nice way. So let's fix it. Let's take the actual quantum state that they have and replace it with the state that's square root of epsilon close to it, the APR pair. Let's put in exactly that APR pair and let's fix it. And then the idea would be, after fixing the first game, we can fix the second game, then fix the third game, fix the fourth game, and that's how we're going to try to prove this theorem. But that's no good. I mean, because if we fix the first game by putting in an EPR pair, we've changed the state by square root of epsilon, which means now the probability of winning the second game is going to be omega star minus epsilon minus root epsilon. So we've introduced some new error into the second game. And so now that's fine. I mean, epsilon's small, I guess. But root epsilon is, of course, much bigger than epsilon. And so now when you try to analyze the second game, you only get that the strategy is epsilon to the 1/4 close to ideal. Then when you fix that game, the beginning of the third game, it's only going to be epsilon to the 1/8 close to ideal. And so again, we have a terrible blow up in the error.
So that would at least let you continue for log 1 over epsilon rounds.
Yeah, something like that. Yeah. So this isn't going to work. What we're going to do instead is try to work backwards. We're going to try to fix the last games first and move forwards, and then we're also going to have to move backwards, and then we're also have to go forwards as well. So what we're going to do is we're going to fix the last games first, only the super operators, the measurement operators, and then all the way back to the beginning. And then we're going to fix the states. After we fix the super operators, we're going to fix the states going from forwards to the end. And the reason for that is you can't fix the state at game n. Like, in other words, you can't replace the state at the beginning of game n by an EPR pair tensor something, because it could be that that state is not the outcome of any measurements. Like, there could be no way of getting to that state in the first n-1 games. So you can't throw out the state and put in something that whatever you like. So that's one issue. And I think there's lots of issues of this type when you try to come up with these proofs. But let me sort of give you the intuition though, and how we actually get the proof working. And the idea really just is based on these two facts of EPR pairs. So the first one is just simple to verify that if you have a 2x2 matrix M, and you tensor it with the identity applied to this vector 0, 0, plus 1, 1, that's the same as the identity tensor M transpose on this vector 0, 0, plus 1, 1. You can just check that. And what that means, though, is that anything that's done on the first half of an EPR pair, Alice's half of an EPR pair, can equivalently be done on the Bob's half of an EPR pair, up to a transpose operation. And the second fact is that quantum mechanics is local, which means that anything that Bob does can't affect what Alice sees, which seems to contradict this first fact, but it's true in expectation. So in other words, anything that Bob does and then you average over his outcomes can't affect what Alice sees, because she just sees her density matrix, the same density matrix, independent of what Bob does. And so here's how we can use these two facts to show that, for example, here's how we can use these two facts to show that the last qubit, the qubit used in game n, is in tensor product with the first qubit used in game 1. And that'll just give you an idea of how we show tensor product for all the qubits. And basically what happens is when you play game 1, there was almost an EPR pair there. We measured it, so it's collapsed. It's just like some classical state. And now we play the middle games, and then we play the last game. And the point is, these middle games, Alice's superoperator could be pulled over to be acting on Bob's side after Bob's superoperator for those games by the first fact. And what that means is that they don't affect Alice's state in expectation, which means that this first qubit, which was collapsed, so it's like ket 0 or something, after these intermediate games, it's still ket 0 in expectation, so which means it really is close to ket 0. And now, so at the beginning of this last game, the first qubit is still ket 0, and we need an EPR pair here, something close to an EPR pair, so it can't overlap that state ket 0, because ket 0 has is not entangled with something, and we need a lot of entanglement to play this game. And so that argument implies that this last game really has to be in tensor product with the first game. There's no overlap, despite all these weird arguments that errors can accumulate doubly exponentially fast. And actually, the tensor product structure is completely explicit. It's even nicer than that. We can construct the tensor product structure. We can see what it is, what it has to be. And so let me briefly show you how that works too. And so, yeah.
The argument that you just made sort of went through a series of n guys. Doesn't this apply just what was the need to go through the middle guy? I mean, you're interested in seeing that the last one is unentangled from the first one, but can't we just sort of build up each one from the next? I mean, from the sets that we had before, using this argument, that the second is unentangled from the first, and the third is.
No, well, if you try to do that, I mean, the errors. I think you'd have the same problem I mentioned at first, because all these kinds of statements only hold approximately, and the errors would accumulate too quickly. So that's. If you just try to show the second qubit's in tensor product, so it's approximately in tensor product, the third qubit's approximately in tensor product, the errors would just blow up. Yeah.
Relatedly, this seems to establish something that is like pairwise between game 1 and game n, rather than the entire state of all n qubits.
Oh no, that's just because I'm trying to simplify things. Yeah.
Why doesn't fact 1 suffer from the errors?
Sorry.
Why doesn't fact 1 suffer from the same errors?
Oh, it will. So because we don't exactly have an EPR state, the first fact will only hold up to like square root of epsilon, which means that when we pull these operators over, when we pull these operators over the other side, we're going to lose a factor of n minus 2 times square root of epsilon, because when you pull the operators over, those errors will accumulate. But that's fine if you're not too concerned about efficiency. It's fine. Okay. So here's sort of how we can here we determine exactly what the tensor product structure is, and it's totally cheating. So what I do is we play the first game. So we measure this qubit. So it's collapsed to either ket 0, ket 1, ket plus, or ket minus, whatever the measurement outcome was. It's some classical state now. And then what I'm going to do is I'm going to add an ancilla qubit, just a fresh qubit ket 0. This is my isometry, so I'm embedding the space in a higher dimensional space by adding this ket 0. Then I'm going to swap it with the qubit that was used in game 1. Just swap those two positions. And now I'm going to keep on playing the rest of the games 2 through n, on this part of the Hilbert space. And you see, for free, I mean, sort of by definition, now games 2 through n are in tensor product with this qubit here, with the qubit used in game 1. And they can't overlap that qubit because we swapped it out into a fresh position. There's no overlap with it anymore. So I've defined this strategy, and it is in tensor product. Every qubit is in tensor product with the qubit used in game 1. And of course, we can generalize. We can extend this to make sure that every qubit is in tensor product. Game 1, game 2, game 3, game 4. This is the first game. Sorry. So actually, to make that work, I also need to, if we just swap these two qubits, then this is ket 0, whereas it should have been x1. So I'll also, as part of the isometry, I'll just rotate it into x1. Okay. So this defines some tensor product strategy. The problem is it's not the same as the actual strategy. It's just a random strategy I came up with that is that where the qubits measured are in tensor product. And so we need to argue that this strategy is really close to the ideal strategy. And it's really just sort of a commutative diagram like this. So I want to say that if you play game 1 and then you apply this weird isometry where you add an ancilla, swap the qubits, rotate the ancilla, and then play games 2 through n, I want to say that's the same as playing game 1, playing games 2 through n, and then applying this isometry. Adding ket 0, swapping the two qubits, and rotating it. So that's completely formally what we're trying to prove. And it's quite simple to see how it works. So on the right, I have the actual strategy. Sorry, I have the tensor product strategy. So when you play games 2 through n, you mess up this qubit, potentially. Oops. You mess up this qubit here, potentially. This is the first game's qubit. And so it's no longer ket x1. It could be something different. It could have been messed up. But here, this is still x1 because nothing in games 2 through n uses in still a qubit. Whereas in the actual strategy, games 2 through n mess up this first qubit. This is the qubit that's used in the game 1. And then you apply the isometry. It swaps that out to here, and you rotate in a fresh ancilla into this position. And so we want to show that these two, the left picture and the right picture, are the same. So the tensor product strategy is the same as the actual strategy up to this isometry. And so that's the same, essentially, as showing that this qubit that started out at x1 really stays x1. These should be the same, and these should be the same. And then the left picture is the same as the right picture. The tensor product strategy is the same as the ideal strategy.
Does it come with some error as well with the swapping?
What do you mean?
Like
There's errors
the
everywhere.
fact that we're comparing these two pictures with the swapping in the ancillary qubit, does it come with some, are the two pictures exactly identical, or they actually are different?
No, I mean, they really are different because this state here that I say used to be x1, it's not x1. It really could have changed a bit, and would have changed a bit.
And
Yeah.
would that accumulate also linearly in the number of qubits in the end?
Yeah.
Okay. So what's the difference in this analysis about the error accumulation? Because initially the error accumulate.
Well, here the error is only accumulating linearly. It's not accumulating exponentially or anything. I mean, actually, you have to see how the argument works to see that. But this is sort of the setup to that argument, though. Yeah. Okay, so that's sort of how the proof works. It really boils down just to showing that once you measure a qubit, it collapses that qubit into a classical state, and it stays collapsed from then on. Nobody else can mess it up very much. I think I'll skip over this. This just gives you a little bit more technical details of how the theorem works. What I've said so far is that the strategies of Alice and Bob are together close to ideal, meaning that they're when you apply both superoperators together, it's close to when you apply both the ideal superoperators together. But for the applications, I want something stronger. I want to say that even if Bob doesn't play any CHSH games at all, even if only Alice is playing the CHSH games, her strategies are close to ideal on their own. This will be very important for any applications. So we want them to be separately close to ideal. And I don't think I have time to explain this, but it's really just a two-line proof in this example to show how to, starting with jointly ideal strategy, you can pull out that you have separately ideal strategies. I think I'll skip over the applications too, because Umesh talked about a lot of them. For example, DIQKD, or this delegated computations idea. But instead, I think maybe the most interesting thing for a workshop kind of setting is to say something about some of the open questions. So one of the open questions is about parallel composition of the CHSH games. Do you still have the same kinds of theorems? Another question that we heard from last time too is what happens if you have other games besides the CHSH game? Potentially every game is locally. Potentially every game in which the quantum value is above the classical value, it's locally rigid. I don't think we have any counterexamples. But we don't know, and I mean the reason for understanding that I think is partly just hopefully that you can get a nicer proof to this kind of theorem because it's kind of ugly. A third open question that I think is interesting is to try to make this kind of test much more efficient. And so I've said that we have this polynomial, we have various polynomial blowups, so in theory it's efficient, but it's quite bad. We'd like to be able to show that even if you win even if you have a constant error rate, then similar kinds of theorems should hold. So say you win with probability 84%, so that's 1% off from optimal. Can you still come up with a similar kind of theorem? So for example, you can conjecture that, say you play little n CHSH games sequentially or parallelly, and there's a high probability of winning 84% fraction of them. Is it true that they must share roughly n EPR pairs in order to do this and measure them in some very nice one-at-a-time tensor product way? I think it could be true. I don't know.
You want to sort of use some kind of fault tolerance?
Yeah, I mean that's one idea. Use fault tolerance. Where are you? Hi. Yeah, you can use some sort of fault tolerance idea, or maybe try to put these kinds of theorems on top of themselves. I don't know. It's like it's a much more a stronger monogamy statement is what you need to be able to show. I don't know. I think it could be true. I think it's interesting. Other questions. What if you allow communication between rounds? So, for example, here I'm saying you play these n CHSH games one after the next, but they can't talk to each other. And this is a problem for applications like device-independent quantum key distribution, because in most QKD setups, you generate the entanglement dynamically. Right? So you generate one EPR pair, you measure it, you generate another EPR pair, you measure it, and so on, like that. And this kind of proof doesn't allow analyzing that kind of setup. We need all the EPR pairs, all the entanglement to be present at the very beginning of the day, and then you say these devices don't talk to each other from then on. So you can apply these theorems. And so one question you could ask is there still a tensor product structure? Can you still use this structure to get device-independent QKD, even if you have communication between rounds? If there's communication in a round, then nothing, you can't say anything. And I guess the last open questions is just to come up with more applications, for example, in randomness extraction or amplification, or delegated computation. I'll talk about that on Wednesday. All right, thank you.
So I guess this is a question mainly about the applications of cryptography in QKD. Normally in QKD we like to say the eavesdropper will be happy to get caught with 50% probability if that means she can break the whole key. Whereas your assumption seems to be that Eve is taking some strategy which she's almost certain not to get caught.
Yeah, I see.
I mean, intuitively, the statement, some version of at least the QKD could still work, right?
No, I feel like you can get around this just with classical statistics by repeating it enough times or something,
No, because you can always say, well, I'm going to do some kind of superposition of doing different kinds of attacks, and some of those attacks will get caught, and some of those attacks won't get caught, and then you have to show that somehow there's no interference between these, that it lets her cheat better by doing that.
Yeah, but I think you don't have to worry about superpositions. You just have to worry about you have to worry about some combinations of attacks. I agree, but I think when you break it up blockwise, you can still say things like, if there's a 50% probability of cheating the whole protocol, like with many blocks, then let me say it another way. If there's the converse would be if there's what is it? If there's a small probability of cheating, if there's too large a probability of cheating in one of the blocks, then you can't cheat too much in the full game.
But look, so again, she can do. So this is not a real attack, but it's a counterexample to the sort of statement that you're trying to make, which is she can say 50% of the time I will do honest behavior and do exactly what I'm supposed to. 50% of the time I'll just do something crazy and cheat on all the blocks.
No, but see, then that's fine, because then this block thing does work in that case, because then you can just say pick a random block and you win. So you pick a random block, and in that random block, they had to have had a high probability of winning.
No, but you don't, right? Because in every block, you have a 50% chance of getting caught and a 50% chance of not getting caught.
You need to condition a little bit, so.
Yeah, so what you want is some sort of statement like conditioned on her not getting caught,
Yeah.
then, but I don't know what goes after the then. Okay, anyway.
Yeah. I understand what you're saying. Yeah. Sorry. Yeah.
Just some wild speculation here. So you kind of use the specific properties of this setup to kind of avoid this exponential blow up in error.
Yeah.
Now this is reminiscent of this problem in like state generation. So for example, if you want to come up with a QMA protocol for the graph non-isomorphism problem, one way to do that would be to generate a uniform superposition of all the permutations of a graph. And you can try and construct such a superposition iteratively, but the problem is you get this exponential blow up in your error. So by the time you get there, your state could be not the right one. And I'm just wondering if you could maybe somehow use some ideas here to kind of avoid this exponential blow up in error. This is all very hand wavy, of course, but I don't know what further assumptions you need in order to get that. But I'm just wondering if there is a potential application to that problem.
I don't know. I haven't thought about that. I mean, you could ask sort of how particular are our methods to this kind of situation, and
like it seems like they are, and in all likelihood they don't transfer easily. But
like we use all over the place pulling operations from one side to the other side, back and forth.
Yeah.
Because you have EPR states.
But I wonder if you can ask a prover to send you a bunch of EPR states and test them in some way. I don't know.
Or
Again, this
finesse
is
it
all
another
wild.
way. I don't know. Yeah.
Just wondering whether there are any connections with another aspect of testing an unknown Hilbert space, which is a dimension, like device independent way of testing a dimension. But there, they kind of establish a lower bound on the dimension by violation of some Bell's inequality. Whereas here, it seems like you have an upper bound because you don't restrict in your theorem, restrict the dimension of the Hilbert space. But they use general POVMs, whereas you only assume projective invariance. So do you think there's a connection here? Can make some kind of dimension statement based on the theorem?
No, I think actually they're probably pretty similar. I'm not sure exactly what you mean, but I think they're very similar. These kinds of statements, like we're showing that the dimension really is at least lower bounded by 2 to the n or something. That's probably the kind of thing they try to show too. Yeah.
Do you have some intuition on why, when you have a game with an advantage of a classical, you would expect a rigidity, or is most of that just the most optimistic thing?
No, I mean I don't have it. I just guessed. I think it's because I don't know why. I don't know. I think quantum is kind of rounded, so there's a local. Yeah, it's an interesting question.